Welcome. In this Innovation Fund tutorial, we will walk you through an example of the application of the GHG calculator for a project aiming to manufacture components for renewable energy facilities. During the application for the IF25 call, project proposals are assessed against several criteria, and the greenhouse gases, or GHG, emissions avoidance is one of them. Applicants must estimate the GHG emission avoidance based on the Innovation Fund's GHG methodology, and shall use the relevant Excel calculation tool. Both are published on the funding and tender portal. If you haven't already done so, we recommend reading the GHG methodology before watching this tutorial. If, after watching this tutorial, you still have questions, you can consult the FAQs in the funding and tender portal, or contact our dedicated help desk. The Renewable Energy Sector Calculation tool comprises 10 tabs. Some are informative, others are for mandatory completion. Throughout the calculator and this tutorial, the acronym RES refers to renewable energy sources. In the first Overview tab, you can find overall instructions about the tool and the color coding to identify mandatory cells that need to be filled in when completing the GHG calculation tool for your project. As shown in this colored table, blue cells identify cells where any information, activity data, or consumption data shall be inserted. Light green cells indicate fields where there is a formula or links embedded. No inputs are required. Yellow cells indicate fields where you should select the appropriate option from a drop-down menu. Gray cells are for comments and other information about the data entered. Finally, hatched cells indicate fields where no data entry is required in the tool. This tab also includes additional information about the tool, such as a description of the contents of each tab, the definitions of the acronyms used in the calculator, and a list of the renewable energy sectors and their respective products, which you can refer to when completing your calculations. In this tutorial, I will discuss a hypothetical project in the renewable energy sector. The applicant proposes to build a production facility to manufacture innovative blades. The blades will be installed in floating wind energy power plants. These plants will produce non-dispatchable renewable electricity, which, in the absence of the project, our reference scenario, would be supplied by the grid. This tutorial focuses on 4 main tabs. The 3 tabs that support your calculation, which are the Reference Emissions tab, the Project Emissions tab, and the Assumptions tab, and the Summary tab, which I will start from. The Summary tab, which you now see on the screen, is mostly populated automatically with inputs from the other tabs. This is also where you will find the final values that you will insert in your application. The absolute GHG emissions avoidance and the relative GHG emissions avoidance. You should start preparing your calculations by filling in the general information table. This should include the sector of the project, and the principal product of the project, as well as any other relevant parameters. I will now move to the Assumptions tab, where I have already pre-filled information about the hypothetical project. As your project is not yet up and running, you will need to adopt assumptions to predict your operational performance and calculate your reference and project emissions. These assumptions, and the rationale for any qualitative or quantitative premises, must be documented and properly referenced in this tab. For projects in the renewable energy sector category, reference emissions are tied to the amount of energy that will be produced by the project. As per the GHG methodology, we assume that without the project, this energy would be supplied by the grid. I will start by listing the assumptions used to estimate the amount of renewable energy generation. In this case, the applicant aims to manufacture 150 blades per year to be installed in wind turbines. Each turbine will have 3 blades and an installed power of 12 megawatts. Based on evidence from known sites, in the location of this hypothetical wind farm, we will achieve a capacity factor of 45%. This assumes the project is at an offshore site with sufficient wind resources. The turbines are expected to operate over 8,400 hours per year. These are the assumptions that will support the calculation of our reference emissions. I will now walk you through the assumptions that will be used in the calculation of our project emissions, which have also been pre-filled in our example. These assumptions relate to the consumption of fuels and electricity that I anticipate for the project site, as well as for maintenance of the wind plant. In our hypothetical example, the wind farm will be supported by a small inland base of 20 square meters. This will serve to store machinery for maintenance and for administrative purposes. This inland base will consume electricity. We will also have a simple boat with a diesel engine, traveling weekly to each turbine in operation for maintenance purposes. I have added these premises to my assumptions table and included some illustrative sources and references for this data. During your application, you must provide adequate and verifiable sources of information and add hyperlinks when possible. Now that we have the data to support our calculations outlined and documented, we will move to calculating the reference emissions. In this example, the reference emissions will be calculated based on the amount of renewable electricity produced by the project, which, in its absence, would be supplied by the grid. 4 rows need to be completed for our example. In row 34, we will calculate the yearly electricity production per component. Row 37 presents the number of renewable energy components manufactured by the project each year. Row 38 presents the years of use of the manufactured component. And row 39 presents the cost of the innovative component as a fraction of the total cost of the relevant facility. Let's start with row 34. I will use the information in our Assumptions tab to perform the calculations. The amount of energy generated by each component, in year 1, will be the power per blade, which is 4 megawatts. I estimated this based on the installed capacity of a turbine with 3 blades, multiplied by the typical plant load factor, which is 45%, multiplied by the typical operating hours, which is 8,400. This gives us 15,120 megawatts hours. In this example, we will assume these operational characteristics will not change over the years. I will replicate the annual electricity generation for the other years. A calculator filled clearly and correctly will facilitate evaluators' review of your project. Please always link calculations with the values in the Assumptions tab, if possible. I will now move to the inputs in rows 37, 38, and 39. I have assumed a scale-up of the production over the first 2 years. The manufacturing plant will reach its full capacity in year 3, to produce 150 components each year. I assumed that each component produced will be used over 5 years, and added the estimated fraction of the cost of the blades in the total cost of the turbine, 20%. Numbers should now be showing up in the green cells to the right of column Q. They multiply the yearly energy generation by an emission factor for the reference grid mix. You can see the yearly GHG emissions calculated for the reference scenario here. This is all the data that is required to calculate the reference scenario emissions. Before we move to the next steps, I want to show you that the tab allows you to add information about the traceability of the data. In these fields, you must provide a brief description of your monitoring plan. It should include data sources, monitoring frequency, and QA procedures. Notice that your total reference emissions are now visible in the summary table at the top of the screen. Having calculated the reference emissions, we will now calculate the project emissions. Before you start, I recommend you go through the parameters to understand what each of them refers to. We will perform our calculations below row 43, as our hypothetical project manufactures components for renewable energy generation. As mentioned, our hypothetical project foresees two emissions sources for the on-site operations. The consumption of diesel in maintenance boats, which I will calculate in row 54. And the consumption of electricity in the small inland base, which I will calculate in row 57. Note that, by on-site, we mean at the power plant using the innovative technology, and not at the production facility producing the components for the innovative technology. As you might recall from the methodology, the emissions due to the manufacturing of the components are out of the scope of GHG avoidance calculations. You can see the multipliers here as well, in rows 62, 63, and 64. The parameters we have in the Reference Emissions tab are automatically repeated here. I will start my calculations for the project emissions in row 54. The fossil fuel consumption in the project scenario relates to diesel combustion in the boats that will be used for maintenance of the offshore turbines. I will add here what I estimated as the average annual diesel consumption in the boat, per blade, in terajoules. To facilitate the review of my calculations, I have already made my conversions in the Assumptions tab. I calculated this value based on some of the other inputs you can see in my Assumptions tab, which are the number of blades per tower, the size of the wind farm, the average distance between the port and the wind farm, the number of trips to the wind farm per year, and the amount of diesel consumed in the boat per kilometer traveled. I will assume this consumption will remain constant throughout the years. During your application, make sure to indicate any expected variation over the years, whether in the fuel usage or frequency of activities. In row 57, I will calculate the amount of electricity imported from the grid and consumed at the inland base. I will divide the electricity consumption in kilowatt-hours per blade by 1000, converting it to megawatt-hours. I estimated this value based on the size of the wind farm, the area of my inland base, and energy use benchmarks per floor area. I will again replicate the calculation for the other years. Now that we have filled all the parameters, we can see that emissions are being calculated in the light green calculation columns to the right of column S. Do not forget to fill in the data traceability columns, and to check the project emissions calculated in the summary table. We are now done with our calculations. Back in the Summary tab, after we have calculated our reference and project emissions, the indicators informing the two GHG emissions avoidance criterion will be automatically calculated by the spreadsheet. These are the absolute GHG emissions avoidance, calculated as the difference between reference and project emissions, and the relative GHG emissions avoidance, calculated by dividing the absolute reductions by the reference emissions. If you can see these two numbers, congratulations! You have successfully filled in the calculator tool. You should now use these results to fill in your application form. You will see that this tab includes other informative fields. You can use them to calculate the emissions intensity of your project, or how much your project will emit per unit. We invite you to revisit the calculator on your own time, particularly to familiarize yourself with the additional tabs that are part of the calculation tool. I hope you find this tutorial useful. If after this tutorial and reviewing the tool, you still have questions, please do not hesitate to submit a question via the help desk, if the answer to your question is not included in the FAQ, available on the Funding and Tender portal. Please note that the help desk can only answer questions related to the methodology or the use of the tool. The help desk team cannot review calculations or validate assumptions that you intend to use for your project. Thanks for watching. Have a great day.